So our first speaker is Adam Harper from Warwick, and you see his title there. So over to our technical division.
Okay, can you hear me? Yes. Okay, so I'll begin. Thank you very much for the introduction, and thank you to the organisers for inviting me to speak here. It's a great honour to be asked, and I'm sorry I wasn't able to come in person. So one of the reasons I couldn't come in person is that I was at another conference last week, and one legacy of that conference is that my throat is now pretty bad, as are the throats of many other people who were there, unfortunately. So given that's the case, more than usual, I would encourage you to please interrupt, if that's possible, with the technology. I'm not quite sure what the setup is, and ask questions, both for pedagogical reasons and also because that will give my voice a bit of a rest and give you a better chance of making it to the end. So the plan for the talk, there are several talks today, this one and the immediately following one, which are explicitly about multiplicative chaos, and some other talks later which are chaos adjacent, let's say. So what I hope to do here is to explain quite roughly, so just in maybe 2 slides, what multiplicative chaos more or less is. So this will miss out lots of interesting subtle points. Some of them might be picked up in the subsequent talk. But this should be enough to hopefully help you understand roughly what people are talking about when they say multiplicative chaos, and also for the number theory connections. And it will turn out that for many of the number theoretic problems that have something to do with chaos, not all of them, but many of them, it's the particular case of critical chaos that's most relevant. So I want to explain to you what that means, what the critical chaos is, and why it's that one that comes up quite often. And then I want to talk about several number theoretic settings and problems that turn out to be related to multiplicative chaos, and also state some results for you that involve chaos ideas or related ideas. I won't say much about proofs. I'll mention a few ideas. I want to try and kind of advertise that there are lots of questions that look like hopefully interesting number theoretic questions. I hope everybody will find at least one of these questions that I think looks interesting, which are related to this thing called multiplicative chaos. Okay, so here in about 2 slides, what is chaos? So multiplicative chaos is a big class of probabilistic objects first studied maybe by Riemann in the 80s. And the idea is that you have some collection of random variables x of h indexed by some set or some space mathcal of h. And you want to form a random weighting or a random measure from these x of h's by integrating things against the exponentials of these x of h's. So you take some test function g, and you look at the integral of g of h against the exponential of gamma x of h, where gamma is a parameter. I've written here that gamma is a real parameter. That's usually true, but nowadays that's not always true. People look at complex gamma as well. So in the probabilistic setting, there are lots of interesting things and lots of more things that need to be said here. So this mathcal h could be quite an interesting set or quite an interesting space. It could be high dimensional, it could have interesting geometry. The number theoretic setting, very often it will suffice to think of h just as an interval on the real line, so something pretty boring. Similarly for the test functions, so in the probabilistic setting, if you want to try and really understand this as a random measure, you want to look at these quantities for quite general class of test functions g. But for number theory, again, very boring choices of g will probably suffice. Just constant g will often be enough. So you can just think of that. And there's also a point about these random variables x of h. So in the number theory setting, usually there'll be some other parameter in the problem, let's say t, if we're looking at the Riemann zeta function around height t on the critical line. And these random variables x of h will depend on t. And we'll want to get information about these kinds of integrals in a way that depends on t. But at any given point, you just have one collection of random variables around. Whereas on the probabilistic side, what people tend to be interested in is you have some overlying set of random variables, and then you regularize them on various scales. And you want to understand, and you perform some limits in this regularization and get a genuine random measure out. So on the probabilistic side, there are lots of interesting things. There's this regularization issue. What class of test functions can we take? What's the geometry of H? But for the number theory side, everything can be very down to earth. So H is probably just an interval. G is some very dull function, like just a constant function. And X of H is just some given collection at any one time of random variables. Okay, now, as I've described this, it's extremely general. To hope to have some nice structure here and to have some theorems, you need to impose some more conditions on the X of H's. So it's usual to assume the X of H are Gaussian random variables. Not at all because this is the only interesting case, but because if we can't understand Gaussians, usually we can't understand anything else either. In the number theory setting, we rarely have exactly Gaussian things around. We have approximately Gaussian random variables at best, but that's okay, it turns out. It's also usual to assume that these X of H's for any given H, they have mean 0 and the same, or at least same order of magnitude variance. So if the mean is 0, then this is the variance, the expectation of X of H squared. So why is that a sensible assumption? Well, if I look at the integral here, I look at the expected, the average contribution at a point H. I need to compute, this G of H is just deterministic, so I need to compute the expectation of e to the gamma X of H. And for Gaussians, you can just do that and you find out that it's this. So if the expectation of X of H squared is bigger, then you get a larger average mass, a larger average contribution from those points H. And if there were some points that contributed on average much more than other points, it would be more sensible to kind of separate those points off by themselves and analyze their contribution separately, because they'll be doing much more of the work in the interval. So assuming that these variances are all the same or all close means that you have a kind of similar role played by all the points H in the interval. And then the other thing is that we want the covariance between these X of H's, so the expectation of X of H times X of H prime. So if the X of H is a Gaussian, this is a measure of the dependence between these random variables. We want it to decay in a logarithmic way as the distance between H and H prime gets bigger. So think of the set H now as being an interval on the real line, let's say. So when H and H prime are close, these random variables should be highly correlated, highly dependent. And then the correlation with dependence should decay, should go away. It should do that in a way that's logarithmic with this distance. It turns out that this is the kind of dependence structure that you need to get some really interesting behavior from these integrals and the corresponding random measures. So let me just emphasize again, these explanations are not going to be independent. Okay, they're dependent, and this is the kind of dependence that we should want them to have, this logarithmic decay of the covariance. And then these integrals are one kind of statistic, one kind of object you can look at, in which the nature of the dependence, the nature of the correlations is possibly going to be important. We want to try and understand how these integrals behave, and understanding the interaction of these X of H's is going to come into it. There are many other questions of this type that you can ask. So you could also ask, for example, about the maps or the sup of the X of H's. To understand that, you also need to understand something about the nature of the dependence between the X of H's. And these questions are related. So I won't get too much into this, but one of the talks that's coming later today, I think, will be about the maximum of the Riemann zeta functioning short intervals on the critical line. And that's this kind of question about the sup over points in some interval of some random variables, some things that you can treat as random variables, think of as random variables. And these problems are related because when gamma gets bigger, this is something I'll come back to later in the talk, these integrals are going to be more and more dominated by the largest values of stage. So if you can understand these for suitably sized gamma, suitably large gamma, that might give you some information about this. I don't really want to get into this in this talk, but if you don't like the look of this and you think this is more natural, well, there's a connection between these things if you vary the parameter gamma. Okay, so in a nutshell, in 2 or 3 slides, that's what multiplicative chaos is. It's about looking at these kinds of integrals, again, exponentials of Gaussians. So are there any questions about what I said so far?
Yes, please go ahead.
Can you hear me?
Not very well at the moment.
I'll repeat the question if it's short.
Yeah, what is the space in which all these test functions are being taken?
The question was, what is the space in which all these test functions are being taken from?
Yeah, so for the purposes of the number 3 things I'm going to describe, just think of g of h being a constant or a step function. That will be enough. In the proper probabilistic multiplicative chaos setting, you need to think more carefully about that. But for my purposes here, very simple g will be enough.
I want to ask, what's the origin of the name?
The question is, what is the origin of the name multiplicative chaos?
Yeah, so Kahn studied these measures as a kind of another version or a generalization of some measures called cascade measures, multiplicative cascade measures that have been studied in probability mathematical physics before this in the 80s. So I guess that's the origin of the name, roughly speaking. These are an extension or a generalization of some other multiplicative measures that have been studied before.
结果不出惊服所料，光在我脑袋里长了一颗肿瘤。虽然不是恶性的，但不及时治疗就可以不会及时愈合。最好的方法就是尽快手术，可手术成功的几率只有1半。
Okay, shall I continue?
Obviously, it's a very popular talk across the world. Any other questions? Do continue, Adam. Thank you.
Thank you very much. Yeah, the more interruptions, the better. So any language, any time, I'm happy. Right. So what's the connection of this with number theory? So I want to say a little bit about this, but just the quick version, because I know it's relatively early in the morning there. So as was mentioned in Sam's very nice talk yesterday, as t varies, we have this result, the Selberg central limit theorem, which says that log mod zeta behaves roughly like a Gaussian random variable. And if I look at log mod zeta, the pointer half plus it1 and the pointer half plus it2, these will be correlated, so statistically dependent, not independent, as long as t1, t2 are, let's say, within distance 1 of each other. And let me maybe just talk about this a little bit. So in the analytic number theory community, people often seem to say that zeta half plus it and zeta half plus it plus ih behave sort of independently once the distance between the imaginary parts is more than about 1 over log t. And I think a reason that people say this is if you compute shift of moments of zeta, so moments of a pair of zeta times a pair of zeta with a little shift, these start to behave sort of independently once you shift by more than about 1 over log t. But that doesn't mean that these random variables, the log mod zeta, actually behaving independently as random variables. Okay, the shift of moments of zeta, of the exponentials of these things, are much dominated by very large correlations. So the correlations might start to go down once these points t1, t2 are more than about 1 over log t apart, but there are still definite correlations there, even on this kind of. So if you're an analytic number theorist, you don't take much else away from this talk. Maybe this is one thing to take away. So these are not independent just because t1, t2 are more than about 1 over log t apart. They need to be a reasonable amount further apart than that to be actually independent. Okay, so these log mod zetas are roughly Gaussian. there's some correlation structure, some interesting correlation structure between them on this kind of scale. So if I look at the integral of test function, a boring sort of test function against the exponential of gamma log mod t, exponential of gamma log mod zeta, this might possibly be related to multiplicative. It's not certain because, okay, the log mod zetas are roughly Gaussian. It turns out they do have roughly the same variance, a half log mod t, for all these points h. It's not clear that the correlation structure, just because there is some non-trivial correlation structure, it's not clear it will have this logarithmic form. But it turns out actually that it does. And that's why there's this connection between multiplicative chaos and various problems involving, for example, the Riemann zeta function on critical. Okay, so that's the quick version. So you don't take anything else away from this big of a talk. This is why there might be a connection between the zeta function, say, and chaos. Here's a slightly more involved discussion. So let's suppose we're in this setting. So I have some family of functions of the complex variable s. So this family is indexed by little j. I want to suppose these functions have, first of all, an Euler product structure. So each fj is either exactly or at least roughly a product over primes. And I want to assume as well that as I vary over my family, so vary my j, there's some, well, independence would be great, but at least some orthogonality, something like that, between the contributions from different primes in these Euler products. And I claim that if we're in this situation and we start trying to integrate test functions g of h against powers of these fj, as j varies, this could put us in a multiplicative chaos type of situation. Okay, so maybe to go back to the genuine chaos setup. So here we had random x of h. We want to understand the behavior of quantities like this, the distributional behavior, or the typical behavior, as these x of h randomly vary. So here it's j that's going to be varying over our family. And then we want to understand these integrals distributionally in j, or for most j, or something like that. Okay, now why might this have the multiplicative chaos structure? Why might it have these kinds of properties? Well, so if fj is roughly a product over primes, then log of fj or log of mod fj is roughly a sum over primes. Okay, if the contributions from different primes are independent or orthogonal or something like that, then this is roughly a sum of independent contributions from different primes. So this might mean that the log mod fj's, so this is x of gamma of log mod fj, that these are behaving roughly like Gaussians by the central limit theorem, the sum of lots of independent things, with mean zero and similar variances. Now, this is not guaranteed from what I told you, because I haven't told you anything about the kind of normalization or centering or anything of my fj's. I've just assumed that a half is going to be the correct spot to look at these, but in a lot of the natural problems, it will be. And then do we get this logarithmic covariance structure? Well, it turns out that we do. And this is because of something that Sam briefly mentioned at the end of his talk yesterday. So in the Euler product, you have contributions from different primes. You have terms like p to the ih for lots of different primes p. And I can write p to the ih as p to the ih log p. And then I can think about how much do I need to shift h to get this to start to move around the unit circle. And if h is less than about 1 over log p, this will still be pretty close to 1, so it won't have moved very much. But once h gets bigger than 1 over log p, then I start to rotate around the unit circle. And so what this means is that for the small primes, where 1 over log p is pretty big, I can move h quite a lot and not really see any decorrelation in that contribution to the Euler product. Whereas for the larger primes, where 1 over log p is quite small, I can shift H by just a little bit, and I start to see some decorrelation in the contributions to the Euler product. And this multi-scale structure, this is very common in problems about log correlation. So this gives rise to the logarithmic covariance structure that's interesting and that produces multiple. Okay, maybe any questions about that before I get on to some examples?
Any questions? No, do continue, Adam.
Thank you very much. Right, so now I want to explain or mention 4 examples of problems that I hope look fairly number theoretically natural and which come into the framework that I was just describing. So maybe the simplest one would be we could take a genuine Euler product, so product over the primes up to some x, say, and also some genuine randomness. So I'll take the coefficients f of p in the Euler product to be independent random variables, let's say uniformly distributed on the complex unit circle. So again, something like this was mentioned yesterday, although in that case, the f of p's or the x of p's were just plus or minus 1. So here it's more natural to think of them as being complex values on the complex unit circle. And then we could study integrals of test functions against powers of this. And this is clearly in the previous framework. This is a genuine Euler product, and we have genuine independence of the contributions from different points. So you could certainly hope to see some chaos type behavior. Okay, so another example, which I already mentioned, is this one. So instead of integrating against a genuine Euler product, a random Euler product, you could integrate against powers of the Riemann zeta. Okay, and the Riemann zeta function on the critical line is certainly not an Euler product. Apart from anything else, it has zeros, which are finite Euler product would have. But for a lot of purposes, especially some kinds of statistical questions, we expect it to behave a lot like Euler. And it will turn out that indeed you do see some multiplicative chaos type behavior for these kinds of integrals. And there's nothing really special about the zeta function and the averaging over t here. So you could also, if you like, look at something like this. So we need to keep a short spatial variable. This is what puts us in the chaos situation. This is what gives us a correlation between nearby h's. But instead of looking at varying t with the zeta function here, you instead vary, let's say, over characters prime or q, and look at the L function on this short interval. So there's another setting where you might see some chaos behavior. Okay, now something else, which is less obviously related immediately to chaos. What I can do is take my independent random uniform on the unit circle f of p's and extend them to a function on all the natural numbers n in this multiplicative way. So to make f of n, I multiply together the appropriate powers of f of p for all the powers of p that divide n. And the object that you get by doing this is called a Steinhaus random multiplicative function. So for example, I know it's pretty early in the morning, but 12 is 2 squared times 3. Everybody's agreement about that. So f of 12 is f of 2 squared times f. And there are, my opinion, at least lots and lots of interesting questions you can ask about sums of these random multiplicative functions. You can ask about their moments, ask about their distributions, so either limit theorem type questions or tail bounds, large deviation results. Ask almost sure bounds. And we now have pretty good understanding of the moments, reasonable understanding of the large deviations, although still not distributional limit theorems like a CLP. And we have almost sure bounds, but they don't match. The almost sure lower bound is possibly close to sharp. The almost sure upper bound doesn't match it at the moment. But all of the best results we have on these questions basically involve somehow a connection to multiple chaos, and involve chaos ideas. I want to try and explain that in the case of the moments a little bit. So by the moments, I mean the same things that the moments always mean, the power averages. Just look at the average of the 2q power of these sums. And okay, so this is a sum up to x of some oscillating things. And we usually expect a sum like that to have size kind of roughly square root of the number of terms. So roughly square root x. So I think I'm taking the 2q power, so it would have size roughly x to the q. Okay, so here's x to the q. So you can show that this average is something involving q, which you don't need to worry about, x to the q, and then an expectation. And just notice in this expectation, we have something exactly like the kind of multiplicative chaos. So we're integrating over a short interval, power, in this case, the second power of an Euler product, a random Euler product. So this thing inside the qth power here is exactly what we had in example 1, with g of h just being the constant function 1. Okay, so I'm not going to properly explain how you prove this. It's not a trivial thing, but it's not super difficult either. You need a conditioning argument and a bit of kind of standard analytic number theory stuff. But what I do want to point out is the exponent 2 here. So whatever moment you're trying to compute on the left-hand side, you always get the second power on the inside here. So the chaos that you need to understand is always the one with gamma equals 2. The q goes up here. So the exponent 2 has some special significance in these problems. Okay, so I'll come back to that in a minute. And then one final question, which I think is maybe the most classical analytic number theory looking question of all these things I mentioned so far. So you could just look at moments, power averages of sums of Dirichlet characters. Okay, so look at the 2q power of the sum of a Dirichlet character up to x and average over all the non-principal Dirichlet, and try and figure out how this behaves. And why should this be related to chaos? Well, this kind of average here, the 2qth moment of the sum of the random multiplicative function, is related to multiplicative chaos because of this. And we can think of this as a kind of model problem for this question here. The random multiplicative function is a random model for the Dirichlet character, which is multiplicative, but also has a periodicity property. So maybe, and it will turn out it's the case, if there's a connection with chaos here, there is, then there's a connection with chaos in this very classical looking number theoretic question as well. Okay, so maybe again, are there any questions at this point?
Is there anything known about like random Hadamard products or random hybrid Euler Hadamard products?
The question is, Adam, is there anything known about random Hadamard products as appear, for example, in the hybrid formula?
Yeah, so I think the answer to that is no. Perhaps partly because I'm not exactly sure what a random Hadamard product would mean in this setting. So it's pretty clear how to make a random Euler product. You take a deterministic Euler product and you put some nice random weights here. To make a random Hadamard product, which is to be a product over zeros, you need to randomize the zeros. I guess you could take a random matrix model the zeros. I'm not sure it's been done certainly in a hybrid way. Don't think it has. Yeah, but you could think about it certainly.
I mean, to some extent, that's a characteristic polynomial of a random matrix.
Right, but that's not the hybrid aspect, right?
It's true. Any further questions? No, Adam, do continue.
Okay, thank you very much. Right, so far I've tried to sell you that chaos is great because there are all these problems. Hopefully at least one of them you think looks interesting, which I claim have something to do with chaos. And at least I've tried to tell you what chaos is. So when somebody starts talking about chaos, you can say, I roughly know what that person's talking about. But so far it's all just kind of jargon. So now I want to talk to you a bit about how chaos behaves. And again, there's a huge amount of stuff you could say here, lots of interesting geometric properties of multiplicative chaos. Might hear about some of that in the next talk, maybe. Well, I just want to talk about one very particular thing, which is what happens as this parameter gamma increases. So I showed you earlier that if you look at the expected contribution from e to the gamma x of h, this is what it is. You can just compute it. And so it increases as gamma increases. But you can say more about it than that. And Sand actually mentioned something like this in his talk yesterday when he was talking about moments of the Riemann zeta function, the classical moments over big intervals on the critical line. So the reason that this gets bigger as gamma increases is because these averages are more and more dominated by very large, very rare values of x of h. So as gamma goes up, it really boosts, inflates the contribution from very big values of x of h, but these very big values become very rare. So Sam said yesterday that the dominant contribution to the 2kth moment of the Riemann zeta function on the critical line is from values of zeta of size about log t to the power k. So as the moment gets bigger, you're looking at values of zeta that are bigger and bigger. And it's the same thing here. So as gamma goes up, these averages are dominated by bigger and bigger values of x. Okay, now in the classical case of these long-run moments of zeta, although these values of the zeta function are big, they're not actually that big, and you're averaging over a very large interval of t. So you'll still, for any fixed k, find quite a lot of values on these big intervals where the zeta function is that large. But here, if you think that we have a short integral here, this is integrating from -1/2 to 1/2, let's say. Once gamma gets big enough, this average will be dominated by values of x of h that are so big that we probably won't find any of them anymore on our interval of length 1. And the value of gamma at which that occurs, where the dominant contribution to these averages comes from values that have become so rare that usually you never see any of them, this is called the critical value of gamma. And what it is depends on the variance of the x of h's and the space that you're integrating over and all sorts of things. But what happens is that provided you're less than this critical value, so provided you do usually see a reasonable number of points h on this interval that make significant contributions to this average, you can get non-trivial behavior just by rescaling this thing in the obvious way by the expected value of the expectation here. But at the critical exponent, that's no longer true. So at the critical exponent, if you rescale this in the naive way by the pointwise expectation, remember we were assuming that these expectations were roughly the same for all h. So this is certainly a natural thing to renormalize by. If you rescale by this, you'll just see that this integral is usually very small. What you need to rescale by to get something non-trivial is something a little bit smaller. So not this exponential, but this exponential divided by the square root of the variance. So this is the interesting thing that starts to happen at the critical exponent. You need this non-trivial renormalization by something a bit different than you might expect to renormalize. Okay, and then, so lo and behold, it turns out in the examples I was describing to you, the critical exponent is 2. So remember, we always got a 2 here. Whatever moment we were trying to understand, it was the chaos with gamma equals 2 that we needed to work with. 2 turns out to be the critical exponent, this way of setting things up. And what's the square root of the variance? Well, for Mertens type reasons, the square root of the variance, the square root of sum of volume of p, grows like a square root of 1. So a characteristic feature of results involving critical chaos is that you'll get some saving factors that you might not have expected of size like log or some power of log. Okay, and that comes from here, from the fact that it turns out it's not at all obvious but it turns out that at the critical exponent, which is the one that's often of relevance for number theory problems, you need to perform this non-trivial rescaling. Okay, so we'll just say a tiny word about the proofs. So what do you do? Where does this excuse me, where does this extra saving come from? So you impose some a priori restrictions on your x of h, but not just on the x of h, on also some sort of substructures of the x of h. So if you think of e to the x of h as being something like an Euler product, you impose some size bands, some growth bands, not just on e to the x of h, but also on all the partial Euler products of e to the x of h. And it turns out you can impose such bounds which hold with high probability, but restrict the sizes of averages like this. And this ultimately is where these extra savings come from in the critical. So in Louis Pierre's talk later about the Fyodor-Fieri-Keating conjecture, you might, I expect, hear a fair amount about barrier conditions, because that's something that comes up when you try to understand the maximum of log correlated processes. And this is exactly what barrier conditions are about. So you try to impose a growth constraint, a barrier on the x of h's, and also some subsums, some substructures of the x. Okay, so this is what chaos does. As gamma goes up, the behavior changes. It changes this critical value. And as it turns out, the critical value is exactly the one that we often need to think about in the number theoretic problems. Okay, so on the one hand, that's a bit bad, because it turns out that critical multiplicative chaos is sort of delicate to work with. So you can see that from the fact that you have to do something non-trivial with the rescaling of the critical chaos. The subcritical regime for chaos was well understood for a reasonable amount of time. It's fairly recent, within the last 10 years, I think, that it's been known in reasonable generality that you get non-trivial behavior for the critical chaos by rescaling by this. So the critical chaos is sort of difficult to work with. That's maybe a bad thing, perhaps. But there are some benefits. So one thing is that if the critical exponent comes out to be 2, well, I guess any even integer would be okay. Well, that gives us some squares or other even powers. And analytic number theorists love squares and even powers because you can expand them out. So let me emphasize maybe it's not going to simply come down to expanding everything out, and that will solve the problem. Because if you look at something like this, I want to think about this where q is some general real exponent. So if q were an integer, I could maybe understand this by expanding everything out. The general fractional q, I can't just expand everything, but having an even exponent here means that in some parts of the calculation, I might be able to just open squares and compute things, and that will be good. And the other good side of this, well, it makes it more interesting that we're in the critical case. If we were in the subcritical case, the answers we got would basically just agree with the naive expectation for what the answer should be. Because it turns out we're often in the critical case, you get a bit more saving than you might have expected to have. Just a little bit more saving, but still a bit more saving. And I think that's really interesting. So for the rest of the time, I want to just go through the sort of variety of theorems that have been proved using these ideas and related to these ideas, and kind of show off what they can do. But again, before I do that, are there any questions about what I said?
Yeah, the random variable capital X has to be real random variable, doesn't it?
You catch that, Adam? I think the question was, does the random variable X have to be a real random variable?
So the answer is no. So it's most usual to think of, let's see if I can go back to relevant place. So it's most usual to think of x of h as being real. So you get a genuine measure here. So you're integrating against something non-negative. That's the same reason for having gamma a real parameter. But you can do more general things. So one of the things people are interested in nowadays is imaginary chaos and complex chaos, where you would take gamma to be maybe imaginary or complex. You could take x of h to be imaginary or complex as well. But classically, x of h would be real, and for the number theory applications, usually x of h is real.
Any further questions? No, I don't. Continue.
Okay, so now I'll try and show you some results. So if you look at the moments of random multiplicative functions, I proved some results about this a few years ago. So if you look at the 2qth moment for q between 0 and 1, what do you get? So again, it's the sum of oscillating things up to x. So the rough expectation would be this should have size about square root x. Then we take the 2qth power, so it should have size roughly about x to the q. But that's not actually the answer, turns out. So the answer is x to the q divided by something with a square root log x in the denominator. So you get a little bit more saving than you might have expected to have. And this exactly comes from critical chaos. So the reason that you have the square root log x here is because there's a connection between this and critical chaos. And in the proof, you need to really use the connection with critical multiplicative chaos and use this non-trivial rescaling. And that gives you this extra saving here. And let me emphasize that this is an order of magnitude result here. So this isn't, we save square root log x, and if we worked hard, maybe we could try and save some more. This is the correct answer. So this is the size of this moment up to constant factors. For larger q, you can understand this as well. For larger q, you don't see this this delicate screen factor. Here you get something that's more like what you might expect if you're used to studying moments of the zeta function or unitary L function. So you get a sort of quadratic power of log in the answer. But for small q, you really get this saving that comes from the critical chaos. So in particular, if you take q to be 1/2 here, you get that the first moment has order of magnitude root x over log x to the 1/4. So Cauchy-Schwarz up to the second moment will give you an upper bound for this like square root x, but actually you save more than that. You get a bit more than square root cancellation for the size of these sums. And you get that because of the connection with chaos, so you need to use the chaos ideas to prove this. Okay, now lots of other things that have been done related to this. So instead of looking at the sum of f of n, you could look at, let's say, the sum of f of n divided by root n. You could think of that as a model for the Riemann zeta function on the critical line, because this is like a sort of randomized version of the Dirichlet series of the Riemann zeta function. And there's a nice paper actually of Imoni and Heap and Yao, which investigates some properties of this kind of sum to model, for example, the most extreme values of the Riemann zeta function. But if you want to look at the power moments, this has been studied for a fairly long time. I think first maybe by Conley and Gambert, and then by many other people. And these are called the pseudo moments of the Riemann zeta function. And the reason they're called the pseudo moments is because if you don't like the expectation, for some unfathomable reason, you can also rewrite this for any fixed x as an average, a limit of averages over big intervals t. So this is exactly the same thing as this, it turns out. If you average over arbitrarily large t, you get the same as this probabilistic expectation. And this is a pseudo moment because the genuine moment of zeta would be the same thing, but there'd be some dependence of x on t. Whereas here x is fixed and t grows to infinity independently of x. Okay, so all these problems, gamma is 2 ends up being the thing that comes out. So for all these kind of averages, you can get an expression like this, and you always get 2 as the exponent of the Euler product on the inside, and the q goes on the outside. And what changes is that if you have the root n weight in here, then in this integral, the big contribution, so there's a weight factor in the integral which much biases towards the contribution h close to 0. So you're not genuinely in a chaos situation anymore, actually, because instead of having an integral like this, it's a very short integral around h equals 0 that makes the biggest contribution. And that's very natural because with the root n weighting, this is much closer to actually being an Euler product than you are in this set. But still, you can use some of the same ideas to get the reaction with the Euler product. And it's always gamma equals 2, the square of the Euler product. But there is a fairly natural way to get something else, not just the square. So instead of looking at the average of f of n, or the average of f of n divided by root n, you can look at the average of f of n times some divisor function, or the average of f of n divided by root n times some generalized divisor function. So when alpha equals 1, the 1 of n is just the constant function 1, so you get back here. And for general alpha, this will give you something where the exponent gamma is 2 alpha. So you can get different exponents, you can get non-critical exponents by looking at different alpha. Okay, now what would we expect to see in the behavior of these pseudo moments? Well, they were introduced as a possible sort of maybe model for the moments of the Riemann zeta function. And the moments of a zeta function and for other unitary families of L functions grow like log to the power q squared. So I guess we'd have expected to see that for these pseudo moments as well. And it was known for q bigger than 1/2. So Conway and Gambert, I think, proved it already in 2006 for natural number q. You can expand things out. And then over a series of works, got to be known for q bigger than 1/2. But this range q less than 1/2, it wasn't known the correct order of magnitude. So actually, the order of magnitude of the pseudo moments was an open problem for longer than the order of magnitude of the actual moments, at least assuming R. So there is something non-trivial to be done to understand what's happening. But the reason for that basically is that you need to understand the interaction between this cutoff to the fixed x and the power q and the multiplicative structure of the f of n. So for the genuine moments, x varies with t, the point where you are on the critical line, and you expect the zeta function or partial sum of the Dirichlet series to be behaving a lot like an Euler product. Here it's not so clear with just this sort of fixed piece. How close is it really to the Euler product behavior? Okay, but this problem has been solved recently using ideas related to this and to this by Gersbach. And he showed, so he did it a few years ago, but it was published this year, that log x to the q squared is indeed the correct order of magnitude on the full range of q, so you might find that reassuring. But he also studied different kind of averages where you have this the alpha of n weight here. And depending on what alpha is relative to q, you don't always get the behavior you'd naively expect. So it turns out that for this particular case, the pseudo moments of zeta without any weights, the answer is what you would naively expect to be. But the reason is not a straightforward reason, and you can construct pretty natural variants of the problem where the answer is not what you would just naively expect. The thing that corresponds to the moments of zeta function. And there's been other work on this by Gersbach and Manzuri, for example. So they look at this kind of average where instead of the alpha, you're putting other multiplicative weight functions. So I personally, at least, I commend this to people's attention. There's some interesting issues in this analysis. Right. So there's also been nice work of, for example, Emma Bailey and John Keating, looking at the analogues of these kind of averages. So again, keep looking back and forth between the slides. These kind of averages, average of a qth pair of some integral of the Euler product. So an average for qth pair of some integral of the Euler product, but now not for Euler products, but for characteristic polynomials of random matrices. So they call these moments of moments. There's a moment here, and the other one on the inside here. And they obtained asymptotics for this when q is a natural number and gamma is twice a natural number. that's the case, we can expand out the qth power and also the twice natural number power here and compute things. And then more recently, FAR's handled a more general situation where Q, I think, still has to be a natural number, but gamma can be anything, basically. And there's been lots of other work done here as well. So there are lots of references I'm omitting. You don't just have to look at unitary matrices, for example. You can look at other groups of matrices. So I haven't told you really enough about what multiplicative chaos really is and what the chaos measure is to explain what it means to converge to a chaos measure. But it is possible to precisely define that. And Saxby and Webb a few years ago proved that if you look at the measure, if you look at the thing that you get by integrating test functions against powers of Euler products, this does indeed converge, whatever that means, to a genuine multiplicative chaos measure for any gamma less than or equal to 2. So for any gamma up to and including the critical exponent 2. And they conjectured that the same thing should happen for powers of a zeta function. And in work in progress, Saxby and Webb and I hope that we can prove this for the critical exponent gamma equals 2. So we haven't done it yet, but we're reasonably confident it should work. And again, the critical exponent here, so critical exponent is sort of more difficult to work with because it's the critical chaos with the non-trivial renormalization. But on the other hand, I have a square, so I can at least do some expanding of squares on the inside here. So it turns out that the critical case, the difficult case on the probabilistic side, is the most accessible one on the number theorem. And we hope, therefore, that we might be able to prove something in this critical case. No other case of this conjecture can know. So none of the subcritical cases, for example. Right, let me mention a few other things. So I told you earlier about this problem of power averages of character sums, which is maybe the most classical, the most natural looking number theoretically of all the questions I've mentioned so far. So you can attack this with chaos ideas as well. And for the low moments, you get, as an upper bound, exactly the same kind of results that we had in the random. So in the random multiplicative setting, you get x to the q, the obvious size, with some extra saving of a log factor in the denominator, coming from the critical chaos. And it turns out, and I think this is rather non-obvious, you get some extra saving for the character sums as well. So you don't need to think about short integrals of L functions or funny measures or anything like that to understand what this result says. It's just a result about power averages of character sums. You get some extra saving, and the extra saving comes because there's a connection with chaos. Maybe the only thing to mention here is the extra saving here. It doesn't involve x. It's not log x here, it's log L, where L is either x or r over x. R is the conductor. And why is that? Well, that's because there's a duality between the sum up to x and the sum up to r over x. So the sum up to x here is related, basically the same up to a scaling factor as the sum up to r over x. So the kind of true length of this sum here is whichever is smaller of x or r over x. And so the saving that you get involves whichever is smaller of x or r over x. But that aside, this as an upper bound is the exact analog of what you get for the random problem, what you get for chaos. Okay, so it's an open problem to get a lower bound, a matching lower bound. And this problem I expect is probably rather hard. So if people are interested, I can say more about why that might be. But it's an interesting problem. I think it's worth thinking about. So by a different method, a more combinatorial kind of method, roughly speaking, Pratesh and Munch and Tenenbaum proved a lower bound for the first moment, which is like square root x divided by a certain power of log. So you'd expect square root x divided by a power of log. And if you could get that, if you could get a lower bound that roughly matched the upper bound here, then by comparing these moments for two different values of q, you could deduce that these sums are non-vanishing a positive proportion of the time. That's a standard Holder type thing. And that would basically tell you that Dirichlet theta functions at 1 are non-vanishing for a positive proportion of characters. And that's not known. So usually when you try to prove positive proportion non-vanishing results, you try and use some kind of modification. But because there's no rooting weight factor here or something like that, it's difficult to modify. It's difficult to make this really close to an Euler product. You can remove the influence of the first primes from. But it's not clear how to prove a positive proportional vanishing result in this setting. If you could get a matching lower bound in this theorem, you get it as a fairly immediate corollary. Okay, but this is probably hard, I expect. And you can also look at these integral averages with the zeta function in them, with the square of the zeta function, and prove again the same kind of bounds that you get in the chaos setting. So log t is the expected size of mod zeta squared, and we get this saving factor of square root log t coming again from the critical chaos. Here again, at the moment, there isn't a matching lower bound, but this one I think probably is doable. So it's an open problem here to get a matching lower bound, but you probably could do it. And in particular, if we manage to do this and prove that you get actual convergence to a chaos measure for the critical exponent of the zeta function, then it would immediately follow from that you get a matching lower bound, at least for q away from 1. But that's probably not the most straightforward way of getting a matching lower bound. So maybe say again, so that the naive way to treat this would be to use Holder on the average over t to go up from the qth exponent to the exponent 1, and then just move the integral over t to the inside and use the second moment of zeta, the zeta squared moment. That wouldn't give you this log-log saving. So this band here with the extra log-log saving is probably sharp. This needs the chaos ideas. Okay, again, there's lots of other work related to this. So Argan, Riemann, and Radziwill proved not quite these moments of moments type results, but they proved bounds for various kind of short interval moments of a zeta function up to factors of size log t to the epsilon in many cases that hold for almost all t. And recent work of Argan and Bailey, which we might perhaps hear more about in one of the talks later today, sharpens this for some gamma. Let me very briefly mention a few more things before I finish. So these integrals, maybe they're interesting for their own sake. But as I mentioned earlier, if you look at this kind of thing for suitable choices of the exponent, that can give you access to information about the largest values of zeta on these intervals, which was the subject of the conjecture of Teodor-Vieri and Keating. So 2 is the critical exponent, so it's a reasonable choice for trying to access information about the large values. But still, at the critical exponent, it's not the absolutely largest values that are making the biggest contribution to these intervals. But knowing that that's the case, you can do a bit more work. You can bias the integral a bit, so it is only the largest values that make the big contribution. And if you do that, you can adapt this a bit. You can deduce that for almost all t, the max of log zeta in this interval of length from -1/2 to 1/2 around t will have size at most log t minus 3/4 log t plus something else. And so this 3/4, as Sam mentioned at the end of his talk yesterday, this is the kind of characteristic thing of the Teodor-Vieri-Keating conjecture. This is showing that these values of log zeta aren't all just behaving independently, but there's some non-trivial dependence and non-trivial correlation which you need to understand, which contributes to this maximum. And Argan, Bourgain, and Radziwill have proved even a stronger version of this, where they get rid of this log-log factor. And again, we might hear some more about this, expecting Lupierre's talk later. And then there are many other things that I haven't mentioned at all. Okay, so there are function field analogues of many of the questions I've mentioned, either genuine function field analogues or model problems inspired by the function field setting, which people have studied. I haven't said much about the random matrix theory side at all. And there's lots you could say here. So, for example, the random matrix analog, possibly, of these sums of random multiplicative functions is something called the secular coefficients of the random matrix. And there's been very nice work on that. Most of the problems I've been describing have been either from the start, or it's turned out that they've ended up being basically on the critical line. But you can look at problems a little bit off the critical line as well. You can also look at problems very far off the critical line, but they tend to be less interesting. You can look at problems just a little bit off the critical line as well. They could sometimes prove more in that setting. There are other random multiplicative function questions beyond the ones I've mentioned. So I didn't say anything about almost sure bounds. To get the best results we know about that, you need, again, chaos ideas. They're very interesting short interval questions where, again, chaos ideas might perhaps come into it. And then there are lots and lots of other things. So that's quite a bit for what I want to say. So I hope at the end of this, you think you know roughly what multiplicative chaos is, at least enough to be kind of G'd up for the next talk, where you'll hear, I'm sure, lots more beautiful stuff about it. And you know what results might look like on the number theory side if chaos ideas are coming in. Kind of characteristic feature usually is you get this bit extra log saving than you might expect. And there are lots and lots of number theory settings, and number theory stroke probability settings, and number theory stroke random matrix settings where these ideas come in. So I hope that some people will be interested to find out more about it. So thank you very much for listening, and that's all. Thank you.
And thank you very much. We had a lot of questions during the talk. Time for one or two more.
Yeah, you mentioned about the random multiplicative function. Now, Fourier coefficients of automorphic form don't quite satisfy the condition. So, do you have any work in that direction?
The question was, do you have any results that might indicate something about Fourier coefficients of automorphic forms?
Okay, so that's a question I'm often asked in these sorts of talks. So I personally don't, but I mentioned this work of Gersbach and Manzouri. So one of the things that they are trying to get at by looking at these more general kind of classes of multiplicative functions. So F is multiplicative, D alpha is also multiplicative. And as I said, they look at more general kinds of multiplicative weights here as well. So you can think here they're trying to understand these averages where you have more general kinds of multiplicative, random multiplicative functions coming in here. But one of the motivations for that is to try and model things like coefficients of higher degree alpha. So I personally haven't worked on this, no, but there are people who are thinking about this kind of thing.
Yeah.
Let's say in the case of the random multiplicative function in the theorem, where you have the Q moments up to a constant, is there any hope that you can actually get the constant?
The question was, in the result that you have for Q moments of random multiplicative functions, is there any hope of identifying the constant term, which...
yeah, so I think you'd have to be very optimistic to believe that you could do that in the current sort of state of things. So there's been some quite nice work doing numerics to try and figure out predictions for it. So you would expect this to be asymptotic to some constant times this expression here. And there's been some quite nice numerical work trying to figure out what this constant might be and what structure it might have. But trying to prove anything like that rigorously, I think, would be really quite challenging. So to prove this, there are two things. First, there's this kind of relation here, and getting this in a form where you could have hopes of getting asymptotics where you didn't lose terms like e to the big O1 would be pretty challenging. I'm not sure it could be done. And even if you could, then you need to analyze this kind of average in a way which gave you asymptotics, and that would require really understanding kind of total mass of critical chaos in an asymptotic way. Actually, that might be the more accessible part of this calculation. But I think getting this this approximation here as an asymptotic rather than just an order of magnitude kind of statement, I think would be pretty difficult at the moment.
I think we should draw a line under this now. Thank Adam James for his talk, and then go off to our